Wow, okay, thank you. That was really a long introduction. Well, I want to thank each one of you. You're the heroes of this conference. I mean, it's 6 p.m. After a long, long day, we're still here. So that tells a lot about you and your stamina. And thank you so much. It makes us want to come back. We're trying to close a long day. And in a couple of times during this conference, you heard about the changes that are happening. We need to get prepared. We need our buildings to be prepared. Just the previous session, there was a discussion of, well, we want to study our buildings in the future. Well, that's really the interest of our work. This is performed within a national project that is coordinated by the National Observatory of Athens. It is part of a national research network for climate change and its effects called CliMact. And it's actually addressing these issues of what are the impacts, what is happening as a result of climate change on various different areas, various different economic activities, and well, our interest, guess what? It's on buildings. And that's what we will be looking at, because buildings have been in the past, are currently, and will be in the future among the key players in terms of the energy, in terms of the environment, in terms of these issues that we are struggling and trying to combat. The future will look brighter. The future is portrayed in this graph right here, and you see where we're aiming in a few decades, tomorrow. I mean, it's not very far away. 2050, we want to really squeeze our energy consumption. Buildings will have to do their share, and buildings will have to transpose from being part of the problem to become part of the solution. And that, if you want to look into the future and what that will hold, well, this is right here, the Sankey diagram of the energy balance of the future. You do not see fossil fuels. They're being wiped out. We're crossing them out. We're taking them out of our energy balance. You will see combustion, because biofuels and mixtures will be part of the energy balance, along, of course, with renewables, along, of course, with dominance of electricity. So that's really what we know about the future. Now, guess what? We want to dream. We want to see and have the vision of what the future will bring and what will happen if we take our buildings and transfer them into the future. How will they behave? What will happen? And while we're doing this, we want to learn in the process of how to improve our energy design, construction practices, and installations. Part of the problem is the balance between the envelope of the building and what goes inside the systems. Will this be just a one-dimensional problem? No, it's a multi-dimensional problem, because a lot of things are going to be happening at the same time. The environment, the ambient conditions will change, but also the technology, the systems, the performance will also change, will advance. Every day, every year, we're advancing. So we're getting better with our equipment, more energy efficient, and so forth. And then at the end, we also want to see how this could interact and what would be the net impact result. And at the same time, we want to investigate the seasonal implications. On one side, we're going to have cooling that, as a result of climate change, getting higher temperatures, would expect to have more cooling demand. On the other side, we're going to have less heating demand, less heating energy. What will be the balance between the two, looking at all this? So, once you want to study, and it was interesting in the previous presentation when someone said, well, we don't really know how to model and predict the future. Well, that's true, that's accurate, because They are very, very complex processes that are happening in the atmosphere that will have then an impact on what we usually say the outside weather. You heard the previous presentation, we're talking about temperature, humidity, maybe solar radiation. So what will be the future that we'll be living in and our buildings will be operating under? Well, thank God we have the tools in order to really process all this complex things, interactions that are happening in the atmosphere, and see how that, as a result of different, continuing different scenarios of emitting to the atmosphere and driving with greenhouse gases, the different dynamic phenomena that will happen in the atmosphere, how that would impact the end result. To make a long story short, here we're not going to develop climate modeling and all that, but as I said, we have the tools. So we're going to be looking, and that's the end takeaway here, at two different scenarios. There is uncertainty, that's a certain thing, that there is uncertainty of what exactly will happen and how things will evolve. But if we're going to manage to really bound ourselves between the business as usual scenario, saying, well, nothing's going to change, that would be unfortunate, but it can happen. So the business as usual scenario of continuing emitting the same amount and pumping into the atmosphere the greenhouse gases, and then a more thinking in a positive manner, in a more ambitious scenario, saying, well, we're going to have policies, we're going to implement the policies that we have, so that we're going to hold the greenhouse gas emissions to a lower level. Of course, we have done enough damage to the atmosphere. How would that evolve in the future? So we have these two scenarios that we're looking. We're trying to bound the solutions and what we will learn out of this. For the abbreviations that you will see later on, RCP, it's 8.5. It is one, the business as usual scenario, as we call it. So whenever you see RCP 8.5, that would be business as usual. Things are just going to go on, and we're going to continue with the damage. With the RCP 4.5, we have a more conservative, we stop this bad process, and well, hopefully things will improve. Well, okay, here's the big picture of how we wanted to approach this. This is part of our ongoing work. So, first of all, we want to create the data, the weather data that will be used by our models to run. So, this is not an easy exercise. Although you do have, and you can generate future predictions of the model, we wanted to really match them with what we have currently, which is the 62 location cities, according to our national regulation. And we wanted to match that. There are a lot of difficulties. When you get a chance to look at the paper, remember all the sessions that you attended today in here, they have papers that will be available to you. So it gives you the details of how this exercise was actually performed. But what it ended up, we wanted to make sure that the predictions that the models get were recalibrated and assigned to the different locations that we have according to our national regulation. And then the second part of the analysis is actually dealing, well, when you want to study these complex issues about buildings, how do you do that? If we have, and I'm sure we have architects in here, say, well, Costas, be careful here. Every building is unique. That's true. But if we wanted to run the exercise about all our buildings in Greece, the key that unlocks this complexity and still has and gives you and facilitates the process is with building typologies. Buildings that have within reason resemble or your millions of your buildings that actually exist out there. And that, of course, we have some knowledge in all this. And at the end, for this typical buildings that would quantify the problem, we want to really calculate the energy performance. So the first thing that we did is to use these climate scenarios to predict for all the cities in Greece and create data that can be used then as input to our models, different calculation techniques. Well, how do you describe all this variability? Well, here's the kind of like the best we can do to give you an idea of what's going to happen. We're looking for near term, that's tomorrow, almost 2050, and then the longer term, that's towards the end of this century. Two time periods that kind of like are representative in these predictions that I usually consider in the analysis. Remember, zone A is down south in Greece, the warm area, Crete and most of the Aegean and south of Greece, and then D, the coldest up north in this map where it gives you the distribution of the four climate zones. What the future will bring? Well, mainly the difference will be in temperatures. That's where we will see most of the variations. Humidity, it's going to be changing, but it doesn't really have the trend or the clear trend. As you see here, we're going to be increasing less in the warmer zone, more in the northern zone, because we're talking about differences in terms of percentages. Right, up north it was cooler, now it's going to get warmer, so the percentage difference is higher, and it's going to get even more as we go to towards the end of the century. That's the big picture of what will happen. Now, we're saying about the humidity that will also depend on the temperature. It's if you attended psychrometrics earlier this morning during the day. Well, there is a correlation between the two. So there is no clear trend. Well, it depends on what the temperature will do, but the humidity will also, of course, be variable. What's not going to change much, it's minimal, it's solar radiation. So that, whatever you have in terms of experiencing, in terms of different solar radiation level, it will pretty much remain the same. It's really what's influencing this, it's really the atmospheric condition, clouds, and so forth. So in terms of using and deriving the necessary climate data in our calculations, that was averaged in terms of what's really happening over the entire country. So temperature is your key player in all this that will be driving the differences. For the typology of the buildings, like I said, we cannot address, we cannot identify every single building. That would be mission impossible. So you use the typologies. The typologies are defined in terms of their construction, which is usually related to the time period as a result of the different building construction codes that we have. Then in terms of the location, so wherever they are located, that is linked to the climate data, so that is already addressed by the previous step, and the use. So you have mainly the residential buildings, there you have single family, multi-family, and then the chaos with non-residential buildings, because you have a different variety, different operating conditions, so it's much more complex when you're talking about non-residential. So guess what? We started with the residential sector. That's also important because the residential sector is the biggest piece of the pie in terms of our building stock. And that's also, we have more buildings, more residential buildings. So in a way, just because we have only two typologies, single and then multi-family apartment buildings and so forth, that simplifies the approach, but it carries a lot of weight because it represents a big percentage of our buildings. The definitions of the constructions, the typologies and everything, all these are the little details with the tables there that you cannot read, but it just tells you they're in the paper. So when you get the paper, hopefully you will dig into it. You can see how they were defined, including not only the envelope, but also the systems, because that's part of the game in terms of really trying to analyze the buildings as realistically as possible. They go hand in hand. The policies change. We're trying to decarbonize. What does that mean? We're bringing out our combustion boilers. We're bringing in heat pumps. With electrification is moving in. All this needs to be considered when you project what's going to happen into the future. So, How do you present now a whole, God, you cannot imagine. Well, start thinking. 62 locations, in four climate zones, then 2 different typologies, the number of calculations that have been performed in order to look at the results. Well, it's difficult to summarize everything. We try to do our best in terms of giving you a taste of what's happening. At this phase, the calculations are performed with the easiest in terms of calculation demand procedures. Meaning, yeah, what a popular tool. Well, it's become very famous because it's easy to use. So we're running not with the existing, with the existing libraries in order to identify the present condition. And here is the present condition of the example of buildings. What is it here? I'm forgetting what. For the 21 locations, right, for only climate zone B. So I'm taking climate zone B to present you with some results. All the other locations are, of course, being completed. But this represents kind of like the average. We're kind of in the middle, and whatever detailed results we're looking here, of course, you can say more conservative in terms of the differences in climate zone A, warmer, and more bigger deviations in the northern climate. So this is for pre-1980, so that's the era before thermal insulation, blah, blah, blah. You know, no thermal insulation, higher heat losses, the worst kind case scenario. So the approach we're taking here is, what if this type of building would sustain itself, somehow manage to make it to the following decade? So that's the existing condition, not doing anything. Then run it also with using the different climate scenarios that we set for the different periods, and then also looking at the renovation, because that's part of the approach we're dealing with. So we're taking our existing building, we're improving its operating conditions, thermal insulation, blah, blah, blah. Systems is important that we are moving to the electrification. So in the best case scenarios, we're using the heat pump. So the business as usual, remember, the business as usual just gives you here the EUIs, the energy use intensities. What do you expect? What's going to be happening? What did we say? Temperatures will start going up. So you see, for cooling, that's the first part of our analysis here. For cooling, you see, you will need more energy. Now I can see it. It's happening. Yes, that's really what we will be dealing with into the future. And of course, as you see here, the result, both in terms of we see more significant differences into the future as we move. These are the scenarios that represented 2090 towards the end of the century. Interesting, you're looking at the results that show you the variation. That's an interesting piece of information. I'm not providing you with a single value, as I'm doing here with the averages, but if you look at the graph here, it tells you the lowest and it gives you the maximum, and gives you the average. That's interesting because you see how things change within the same climate zone in the different locations. That explains why it was important as a first step to determine next in each and every city that will be performing the calculations the corresponding results. Because yes, it will make a difference even in the same climate zone of where you are, in what city you are within that climate zone, at least the way they are defined currently in the regulation. Now, the results are also important in terms of policy of what the future will bring to us. It will bring problems. It will bring problems as we move into electrification. And of course, with cooling, we are already electrifying our buildings. That's the way we cool our buildings. We use mechanical equipment that need juice. They need to be hooked up. They need electricity to operate. So that is going to be going up. And we need to get ready. We need to really prepare our grid to face this situation. Well, in a way, the good news is that heating is going to be going down. We're going to be needing, if the ambient conditions are going to be warming up, with the implications that we already saw, the heating is going to be going down. The weather conditions are going to become milder. So the analogy here that you see on the right-hand side, where we have again for the typical pre-1980 type of residential building to the big renovation, the result, the analogies here, yes, things are going to be getting warmer, so that means that heating demand will be dropping. And as you have seen in the previous, when we renovate, which is another takeaway, we have been repeating ourselves that the way to really handle this situation that we're getting into, in several ways, but also financially speaking, in terms of us as users and everything, is to renovate our buildings, fix the problems, and not let it continue bleeding energy and so forth. So you see there are significant savings that we can achieve that will also have and give us the opportunity to have a lower energy demand. You see the EUIs here, the energy use intensity of energy per unit floor area. You see they're dropping down, and now they're becoming more manageable, and also that will allow us to also use and move away from combustion, from burning fossil fuels as we are doing, and putting less load because the demand is going to be coming down if we electrify. Now, we're looking at the results here. I'm not going to spend so much time, but similarly, representative results are also presented for the new buildings. Okay, these are the ones that are most likely to make it in the following decades and still operate because they're just like constructed according to the recent new regulation. So still, is there room for improvement? Yes, there is. In that case, the scenario for the renovation is we bring them up to the nearly zero energy building. So there is room for improvement. Now, already you notice that for cooling, we're down to a much lower EUI. And now, of course, the impact of increasing the outdoor ambient temperatures, well, still, they're going to go up. But still, if you recall, we're in much, much better shape of the older buildings and how they will be performed. Similar results for the heating. So I give you a taste of the energy demand for the different building types for looking at the big picture, not going into the very detail, but I think you kind of like catch the idea, and of course when you get the paper, you can look at the more results. So then the next thing we looked at is that for every city, we wanted to see the energy demand for both the single family and the multi-family. The main high-level observation, there are large variation within the same climate zone. So we're still, and I'm showing the results here, still for climate zone B, and for the cities within that. Look, even from a distance that you cannot tell, I don't know, I don't see exactly what this is, but look at the variation. So these are within the same climate zone. You would say, well, I would expect that they will perform the same. No, this is another interesting takeaway, that the city location, the behavior, the impact is going to be different. What does that mean? Well, at least to me, it means that we may need different approaches, more tailor-made approaches, far and above what, for example, the regulation says that, whatever happens in climate X, Y, A, B, C, D applies to everyone. Well, no, because there are differences, so they have to look closer with this kind of discretizing the analysis and looking at each individual city. That would adopt the minimum requirements. So I would really favor an approach where hopefully in the new evolution of the national regulation, this will start transposing not on the basis of climate zone. I can understand the logic, but the results clearly indicate that there will be different impacts and different priorities for including the minimum requirements, and also specific energy efficiency measures. So what are we going to be suggesting? What we will be promoting should depend and should be based on a per city analysis. In all cases, the most notable benefits, improvements that we would expect, yes, it's kind of like a no-brainer. The older buildings that will be renovated are in biggest need and will give us the best benefits, or most of the benefit, and that should be the priority. And in one more study, that reveals of where the focus should be. Well, okay, up to now we're talking about demand. Now we talk about consumption, which means the systems come into play. So it's not what the building needs only, but who's going to be providing this energy to satisfy the demand. The systems come in, so we're looking now on the efficiency of the system, of the coefficient of performance, and so forth. So bringing and integrating this kind of changes now what we're looking at. So the cooling demand is going up, and that will also have most likely implications. So we have different priorities in terms of when the loads will become. That will be during the summer and during the winter. The impact of the grid will be very important. And when we look at the emissions, that will also have an implication on the type of fuels that we will select. It would have some benefits. The higher cooling demand, that means more electricity in the summer. Well, we can generate more electricity from PVs, for example. I like that. There is a match. Also, the advantage of lower energy demand in winter will give us an opportunity to decarbonize our buildings, needing less energy when we replace our fuel-fired boilers. And that's now what I was talking about, the final energy consumption, representative results for the single and multi-family buildings. For Zone B, as I said, all this has been performed and repeated for all the climate zones and all locations. So while we're doing this and we're fighting our way through a warmer climate, we're advancing with the better technologies, better equipment that are going to be performing in a much more efficient way. Well, that's good news, because what's going to happen is you're going to be requesting that the equipment provide you with more energy. Yeah, right, that will need more cooling, but they will do it much more efficiently. So having better equipment, better technology to address the problem can lower the energy consumption of the equipment. That may counterbalance a little bit of the worsening scenarios and of the higher demand. Of course, all that will depend on the technological advances. It will depend on how fast we renovate our buildings, because we're going to have to get engaged in a race in order to do this. And of course, the minimum energy codes and how strict that will advance, of how strict or how fast we will be pushing the renovation wave of our buildings. Carbon emissions was the next exercise that we run. The results, again, so you and quantify the environmental impact. Here we need to be careful a little bit. When you look at the results and whatever comes out of the TEC and NAC calculations, the regular according to our regulation software, you need to be careful when you look at the results, because they use, the software uses, and the national libraries use it in old conversion factor. An old conversion factor is old 15 years ago. So that takes you back to whatever the energy balance was back in 2010. So things have improved, thank God. The grid is the electricity grid. That's where the main problem is with the electricity. In terms of the emissions, it's an overestimate, the number that you get. But unless you're looking at the absolute number, which is off, it's wrong, and you shouldn't be using it for anything else other than what we are mandated by the national regulation. When, if you look at the difference, well, you can say, well, the difference is okay. No matter what the absolute values are, the differences would obviously be the same when you look at the different scenarios. So that, at least, would be reasonable. So we, again, looking at the present condition between the different time scales that we have in the deep renovation or the nearly zero energy building, where we're talking about the most recent typology, you see we're cutting, of course, about more than half of these emissions as we move into the future because things are becoming more efficient and so forth. So in conclusion now, that's really trying to close in and trying to kind of like wrap up this study. Well, it's tough, but let me tell you again what we did, and hopefully you will find it interesting. We did this exercise for all locations, at least that we are within our energy code, 62 cities in Greece, in the 4 climate zones. We looked at 2 different climate scenarios, the business as usual, and a much better part, something that realistically we can actually implement. Somewhere in that band, that's where we will land. And we started with the residential buildings. For cooling, as we said, things are going to get worse. So they're going to be actually demanding, and you see the numbers there in terms of the percentage of how much, so that you get a sense of, well, if I let it go, even for your own home, what's going to happen in the next decades. And since we're giving the results for 2050, that's really the day after tomorrow. 2090, depending on how old your building is, well, I don't know, maybe it's not going to be steady, but definitely if it's a recent construction, it's going to be there because the lifetime of our buildings are about 50, 60 years, so definitely they will make it to that. So we will need about twice as high cooling energy demand compared to the baseline, compared to today. There will be an increase, and you see the quantified. Well, the big picture, if we want to kind of like, okay, give me something that I can remember before. Well, overall, there will be an increase for the down the road. That's where you really see the maximum 2090 of about 73%. Looking at the entire country. So that's kind of like a significant problem that we have to face. Things are a little bit softer, milder, better, depending, use the word that most likely suits you, when we look at heating. As we said, we're going to need less heating, and again, the analysis is that this may counterbalance some of the issues if you look on an annual basis, what's going to happen. But, well, maybe that's misleading because especially in the period that we're moving, it's a different way, especially when you're talking about renewables, of when you're going to be generating this green electricity. It will be easier in the summer, but it will be harder in the winter. So that, you have to take that into account when you analyze the results. And again, the big picture, when you look at the national average, yeah, the energy demand will decrease. There, you're going to be benefiting about looking again, all the zones, all the types for the different climate scenarios, about 34% less. Now, in final conclusion, when we want to also look at what the future is, that the technological advances will absorb some of this noise, will take, well, not noise, some of these problems. So because we will be having and using more energy efficient, higher performing equipment, we will be demanding less energy. So that's kind of like the benefit of technology advances over the next few years that we can benefit. Building renovation, it is a top priority. That's what needs to be changed, be pushed for the millions of buildings. We have to really upgrade to renovate them, and we have to find, of course, the huge financial resources. Before someone asks, yes, that's we use a simplified tool, like the NAC is a quasi-steady monthly method that is implemented that may be too simplistic for this kind of complex, but we also wanted to get a sense of what is considered the main tool that engineers use far beyond and above the Call of Duty, which is for labeling, auditing, and labeling buildings. So we wanted to get a first feel of it. So that was kind of like the motivation. So the ongoing work now, it's moving into, and that's an ongoing thing that we're doing, dynamic simulations, very accurate tool like Transys, where we want to make sure we capture all this diversified needs, behavior that might happen to really see how they would compare. Let me tell you, you only must know now, things are very compatible between the simplified tool and the simulation tool. So we're not, what you're reading and seeing here, it's not really far away from what you will see, and hopefully soon we will be publishing the results from this simulations. I told you, and I admitted, that when we're looking about emissions, we have to correct. So because we provide some energy, I'm getting tired. The emissions as a result of normalized values, like how many kilograms of CO2 greenhouses per unit floor area, because we provide this results also, we need to be a little bit more sensitive about the accuracy of this result. So we need to correct, as I said, not with today's, with the whole absolute, doesn't exist. The conversion coefficient in Hellenic does not exist anymore. So we need to update, and especially now we need to also project into the future, because every year things are getting better. Every year we emit less, we have less environmental impacts from power generation and so forth. So we would like to couple this results with this projection, and the elephant in the room, non-residential buildings. That kind of like opens a huge task. We're trying to really address the most important types of non-residential buildings. So we have selected 3 types that pretty much give you the diversity and the complexity that at least resemble and reflect the issues that we have to deal with, of course, when we deal with non-residential buildings. Have some references here for you. Don't forget to look up the paper when the proceedings come up. There are a lot more details, and make sure that you also follow up the link that I gave you for this program, because a lot of interesting results will be presented with the final deliverables and reports. And if you're interested, buildings is important, but I'm also interested in other sectors, agriculture, transportation. Clean Pact addresses all these different sectors. So please also check out the website there to see what may, in addition to buildings, be interesting to you. Thank you for making it all the way. I noticed nobody moved, nobody left. So thank you so much for being here with us today. And, we're almost to the end. So thank you.